Here we go. Okay, so let's chit chat about this whole concept of net ionics, okay? And like I said, this whole deal of net ionics, if you ever go in and study more advanced chemistry, especially if you end up taking me again for AP chemistry, net ionics are actually what we spend 90% of the time on. Mainly because of the fact that it just like cuts out the fluff, and you can just focus on what it is. Now, the beauty of this net ionic is that number one, it only shows you what's actually involved in making the new compounds. Okay, it would be like you're watching the Kansas City Chiefs game. Okay, you're watching the Kansas City Chiefs game to see what's happening on the field. CBS isn't going to spend 3 hours just filming people that are spectators in the stands. Nobody cares about the spectators. You know, maybe the kiss cam. Okay, maybe every once in a while. Maybe somebody waving. But for the most part, everybody wants to see what's happening on the field. And that's what net ionic equations do. They show you what's happening in the field, because that's really what all we're worrying about. So nitrates are always spectator ions, because they're never going to make a precipitate. Okay? They're not. So spectator ions we don't care about. Group 1's ions, okay, lithium, sodium, potassium. They're important, but we're not going to care about them because they're not going to be involved in forming a precipitate. Okay? So if you keep that in mind, that kind of gives you a broader idea of why we even worry about these. Now, the other thing is that if you listen to the word, it is a net ionic, okay? Which means typically these involve ions, which means that you have to put the charges on the ions, okay? Because if you don't, and here's the difference. If you have, let's say for example, on number 3 on this lab, okay? On number 3 on this lab, you reacted iron 3 nitrate, okay, with sodium hydroxide. Okay, so let's start with this one, because this is one that's a little bit more complex. All right. So again, if you're really going to understand this, you have to understand the structure of these particles and how they exist. So when I set up this lab, okay, I had to mix up the iron 3 nitrate. So I chose iron 3 nitrate because of the fact that I wanted you guys to have access to iron ions, okay? That's what I wanted you to have access to. If I wanted you guys to have access to elemental iron, I would grab a bottle of iron filings and go, oh, here's a chunk of iron. And we could put that in the lab, okay? It's not what I want. You guys had to have available to you iron 3 nitrate, because that's what allows you to, in that dropper bottle, was kind of that was that one that was kind of orangish in color. So in that dropper bottle, you had a whole bunch of ions, and had a bunch of nitrate ions, okay? And you also had a whole bunch of water molecules floating around. So when I mixed this up, I made out a certain amount of iron 3 nitrate, poured it in some water, mixed it up, it dissolved. So we went from that iron nitrate being bound together as a solid, and they basically got ripped apart. And once they got ripped apart, then it existed as iron ions and nitrate ions, okay? Now, on the other side of that, in the other bottle, you had the base, sodium hydroxide. So you had a bunch of sodium ions, and you had a bunch of hydroxide ions. So these had to exist as separate ions. So what happened was that here was your well plate. And you added some iron nitrate, okay? And then you added to that sodium hydroxide. So these particles are mixing around, right? It's a dynamic situation. So what happened is the iron comes up to the hydroxide. Says, hey, we're oppositely charged. Really not bound with the nitrate. What do you say you and I hook up? And the hydroxide goes, I like you. Okay? You're iron. Iron Man, right? Ooh, it's kind of cool, right? So the hydroxide becomes very attracted to the iron. and it becomes so attracted to that iron. It's like romance on a chemical level. And they become so attracted to each other that they come out of the solution. They go, you know, water molecules, love you to death, but I'm going to be more attracted to the iron. And fundamentally, that's what happens. It's a tug of war. So the iron is attracted to the water molecules. And I know it was attracted to the water molecules because it dissolved. But then it comes along the hydroxide, and the hydroxide is also attracted to the water molecules because it was soluble. And they go, huh, which one do I like more? Do I like the iron more? Or do I like the water molecules more? And they basically go, I like Iron Man. So the hydroxide is going to start to hang out with the iron. So out of this then, and this is why you have solubility rules, and so out of that, you should get a precipitate of Fe3+. So what's going to happen is that out of this, you're going to get your FeOH3 plus your sodium nitrate. Now, make sure that you balance this equation, okay? Simple. Oh, 3 hydroxides, 3 hydroxides, 3 sodiums, 3 sodiums, 3 hydroxides, 3 hydroxides, 3 nitrates. This is FeNO3, there's a 3, okay? All right? And everything is balanced. So that's your normal run-of-the-mill generic equation. Here's everything involved in it, okay? It's cool. Now, when you get done with that reaction, when you get done with that first one, make sure everything is balanced, okay? You're not showing the nitrates, you're not showing the charges or anything funky. This is just your normal run-of-the-mill generic equation. Hey, everything should balance, okay? And again, here's what I've seen happening, okay? Just because you have 3 nitrates over there, when you write that as that sodium nitrate, it's recombining with the sodium. So you have to look at the sodium being 1 plus and the nitrate being 1 minus. That's why that's written as NaNO3. So you have to get the terminology. So we use these subscripts to balance out the oxidation states. We use the coefficients, which are the numbers out in front, to balance the equation. So subscripts occur to make the oxidation states add up to equal to 0. Coefficients exist to balance the overall reaction. Okay? Now, on the second line, this is where you're going to drop your pen and it's going to fall underneath the table. Oh. Hey, that's hard on an old man. Oh. Okay? So, here's going to be the next step. So, you've got to figure out those solubility rules. And again, on the test, by the way, which is Monday, okay, big test on Monday. You're going to have 2 big tests left, 3 big tests. You have this test over reactions, balancing chemical formulas. The next unit is stoichiometry, which is just stoic, is just chemical formulas with math. And then your written final, and then lab final, okay? So you have some big assessments coming up. Monday, big assessment, huge, okay? So you're going to have access to those solubility rules, right? You're going to have access to it. You just have to know how to use them. And again, I don't care which set you use. If you like the ones that are on that, this one, okay, where this is kind of the short abbreviated version of them, if you like this, hey, go with that. If you like the more colorful one, go with that. I don't care. Pick one, okay? Don't care. But just get comfortable with them so you know how to use them. So what you'll see is that most hydroxides are actually insoluble. Unless it's the group 1, it's pretty much going to be insoluble. So come in here, and this is the one that's optional. If you're feeling good about this process, you don't necessarily have to do this second line, okay? But when in doubt, do that. So come in here and go, okay, this is Fe3+, that's nitrate 1 minus, that's sodium plus, and hydroxide minus, okay? So you list all of the ions out, okay, and the state that they're in. Then you go, oh, look at my solubility rules. Now, I know sodium nitrate is never going to make a precipitate. It's like the poster child of solubility. It's got a group 1 cation, which makes it soluble, and you have nitrates, which are always soluble. So there is no way you could have a precipitate of sodium nitrate if you tried. Okay, it's not going to happen. So I know that if there's a precipitate, it has to be that FeOH3, and then you got some sodium ions, and you got the nitrate ions. Okay? So at this point, now you can get rid of your spectator ions. Oh, it's a sodium ion over here, it's a sodium ion over here. It's a nitrate ion there, it's a nitrate ion there. Okay? So I eliminate those because they're there. Okay? I don't want you to get the idea that, well, they're not in the solution. They're in the solution. They're just existing as ions. Okay? So what you have left, and I'm going to write this wrong. What I'm going to do is wrong. Do not do what I'm about to do. It is wrong. Okay? Oh, here's my net ionic. Fe plus OH yields FeOH3. Why is that wrong?
You need to balance it out.
Okay. Better?
Need the charges too.
Yeah, because here's the deal. And this is what you have to understand is that this is a method of communication what is happening in a reaction. If I see Fe, I'm going to think it's a chunk of iron. Okay? Literally, that's what I'm thinking is going to react. I'm going to think this, I gave you a chunk of iron that you put into the reaction. Okay? You got to get it back.
Huh?
What, did you have an escape?
Oh, no, when you drop them, they kind of go everywhere.
Okay.
So I don't know where the other one went.
Okay. What did you drop?
My AirPods.
Oh, okay. Well, been there, done that. Okay. So, here's the deal. There's a huge difference between Fe and Fe3 plus. They convey completely different information. If you just say iron reacts with hydroxide, I'm going to think you took a chunk of iron and you reacted with hydroxide, which is solid, which doesn't even exist anyway, which is physically impossible because you just can't have hydroxides. Okay? But if you go, oh, Fe3 plus, and then you have 3 negative charges, now you're in the wheelhouse. Okay? Because now you're sitting there going, oh, this is cool. So now there's 2 things why this works, and Miles had the first one. You have to balance this on 2 situations. You have to balance it on charge, and you have to balance it on number of particles. And this does both. So I got 3 negative charges, I got 3 positive charges. Those add up to 0, I have 3 hydroxides, I have 1 iron, boom, I'm good. Okay? See the difference. Is he? Yeah. Are we good? Yeah. Okay. Now, let's talk about, for example, on number 7, on that back side. Okay? No. So in number 7, here's the deal. So you had copper nitrate and hydrochloric acid. And out of that, you're going to get copper chloride and HNO3. Okay? HNO3 is nitric acid. Okay? In case you forgot, HNO3 is nitric acid. So basically what's going to happen is that you're going to take copper nitrate and hydrochloric acid, you're going to get copper chloride and a different acid. Okay? You're going to get HNO3. Now, here's the deal. When you look at this in terms of solubility, right away, you know, HNO3 is not going to make a precipitate because it's nitric acid. Okay? That's not going to make a precipitate. So the only thing that could potentially make a precipitate would be the copper chloride. Okay? So this is when you look at your chloride rules and you go, oh, all chlorides are soluble except for silver and lead. Okay? So that isn't silver or lead. So everything here is completely soluble. So you're not going to make a reaction. the only way that you could figure out that you actually made copper chloride was is if you heated it up and you evaporated it. And what you would see is that you would have a residue of copper chloride that was left behind. Okay, that's the only way that you can tell that it's there, because it's going to be floating around. So this won't make a precipitate. You're going to get a reaction. You're just not going to get a precipitate out of it. And the same thing is going to happen on number 8. Okay, so if you look on number 8, you don't have anything because of the fact that your aluminum chloride and your nitric acid are both everything soluble. Yes, ma'am.
On the colorful paper, they have, like, the chloride one, it says that copper is insoluble, like, yeah.
On the color one?
No,
Yeah.
it says copper chloride is.
It said it
Yeah.
was
Oh, it's only got the
precipitate.
1+ next to it, so it might be like copper 1.
I think you're wrong.
Well, okay, here's the deal. That, okay, and this is a 2-day lecture I give in AP Chemistry. So that is based upon, it's a concept known as QSP and KSP. It has to do with equilibrium and a whole bunch of complex math, okay? So that is based upon a certain standard concentration of 1 molar solutions. So typically, under normal circumstances, you don't have that high a concentration of solutions. Like these are much lower than the 1 molar concentrations. So that's why with this one, in reality, this white paper, this one is more realistic, basically in terms of what's going to happen. So with this one, you should not get a precipitate.
Keep one, I had 2.
Okay,
I'm
well, no, I'm good. I
Do you want me to change it on the paper? Or like, on like the.
If you did it that way, that's fine.
Okay,
But typically, they don't, because that's the chlorides, that's the standard thing. That chlorides aren't soluble except for lead and silver, and maybe mercury. There's actually a song that we learn in AP Chemistry about solubility
so I
rules.
can keep it,
Yeah, if you have it that way. It shouldn't have made a precipitate in the lab, because.
yeah, it didn't, but.
Yeah. So, that's weird. They shouldn't have that on that sheet. That's why I hate using other people's sheets. Okay. Now,
Oh, man.
let's talk about number 11. Okay? Let's talk about number 11. So, on number 11, bottom of all of my fixed lecture notes from yesterday. So you got magnesium and iron 3 nitrate. Okay? So right away, when you see an element plus a compound, what type of reaction is it going to be? Single displacement, double displacement?
Single.
Single displacement. Take AP chemistry, we're going to call this a redox reaction. Okay? Lose electrons, oxidize, gain electrons, reduced. So, what's going to happen is that this magnesium comes over here, it kicks out the iron. So, again, let me see that, the color one. Nope, color one. So, you're going to have, on the test on Monday, you're going to have this chart, okay, this reactivity series. You have to know how to use it, okay? So, if you look on this chart, you'll notice that magnesium, okay, is up above iron, right? So that means that magnesium is more reactive than iron is. And by reactive, that's the magic code for saying iron can take in electrons easier than magnesium can. So that chart you have to be able to use, understand it. So basically, you have elemental magnesium, and I'm going to dump that in with this. So when you all did this, here is your well plate. You have the FeNO3. These were these little ions that were floating around, right? And you put in that chunk of magnesium. And right away, you all began to see a color change, okay? Right? Began to change color. So that's one of the indicators that a chemical reaction is taking place. There are certain things that indicate a chemical reaction. Oh, And you all have seen them. Oh, there could be a change in temperature. It could get really hot, it could get really cold, okay? They could make a precipitate, okay? You could have bubbles form. You could see a change in that color. So those are the big indicators that something has happened. And what's happening is that when we reshuffle, and that's fundamentally what we're doing, any chemical reaction is based upon the reshuffling of outer electrons, okay? Nuclear reactions are reshuffling the nucleus. That's what we call nuclear reactions, okay? Chemistry is the study of how those outer shell electrons react. Nuclear physics is how the nucleus itself reacts. So what happened is this. Again, this is a tug of war. So if you visualize this from that perspective, these reactions become easier to understand. So here's that Fe3 plus, and it comes up to that magnesium. So that magnesium, those atoms are stuck together, okay? And I know they're stuck together because it's a strip. It's a solid piece of magnesium. Obviously, the magnesiums have to like each other, and enough that it forms a solid, okay? Nitrogen, we have a lot of it in our atmosphere, okay? They don't like each other. They bounce around. They like, they run into each other like, hey, screw you, okay? They're just going to bounce off of each other. Same thing with oxygen, okay? Which is why our atmosphere is a gas and not a liquid. And thank God, nitrogen, they don't like each other, okay? And that's cool, okay? They don't like each other. Otherwise, we don't have an atmosphere, which would be bad, okay? We wouldn't be here having this discussion. So it's cool that our universe exists where you have things that bounce off of each other and they exist as a gas. So our existence on this strange rock is pretty much dependent upon these little tiny bits of matter and whether or not they like each other. And then that's based upon how do those smaller bits of matter called electrons interact. That's why we exist. That's why we're here having this discussion. So if you look at the early atmosphere, we didn't have oxygen. It wasn't until there was a group of microbes that began to take over and they generated a whole bunch of oxygen gas. If we didn't have oxygen gas in our atmosphere, we wouldn't be here having this discussion. If we had too much oxygen, we wouldn't be here having this discussion. So we kind of have this Goldilocks zone of oxygen and nitrogen. We have an atmosphere, it's nice, it exists as a gas. The magnesium was actually formed in the death, speaking of nuclear reactions. So all that magnesium that you all just used in your lab yesterday, okay, that at one point formed in the death of a neutron star, okay? It collapsed, the protons and neutrons slammed together, that got kicked out, it got spread out throughout the universe, it got recoalesced on this strange rock about 5 billion years ago, give or take about 10 minutes, okay? So we've been here for a while. So this magnesium has been through a lot, okay? It's been through a lot. It was formed in the death of the star. It got kicked out. It got reformed on this strange rock, third one from the sun, okay? So these have been together a long time, and they've been through a lot. It's like, man, we were formed. Like they're talking to each other, going, remember when that star collapsed? About 5 billion. Yeah, that was cool. Actually, it was really, really hot, okay? And then they got formed, and then they got kicked out, and then they got spread out, and then we processed them and we put them all back together into this little thin magnesium ribbon that I tore apart and I gave each some of you. Okay? So that magnesium obviously is attracted to each other. That's why it's a solid. Okay? I'm not going to give you all a chunk of nitrogen gas because they don't like each other. It's a gas. Okay? So it's kind of cool if you think about it from that perspective. So here's this magnesium. They like each other. Okay? That's why it's a solid. Along comes the Fe3 plus. It has a deficiency of 3 electrons, okay? And this iron has been around for a while too. The iron was also formed in the death of a previous generation of stars, okay? So in this solution, here's this Fe3 plus, okay? It's missing 3 electrons, okay? It's 3 electrons shy. It comes up to the magnesium and says, hey, mind if we take some of your electrons? Magnesium says, hey, even though we've been a lot, deuces, you're out. So it takes those 2 outside electrons, Eddie and Edna, okay, and it gives those to the iron, okay? But the iron says, cool, now I've got the electrons. Now it goes back to being elemental iron. So what you saw forming on the outside layer of that strip of magnesium was actually a layer of iron. Okay, it wasn't rusting. Okay, it wasn't like, it kind of looked at an orangish color. That was because of the solution that was in. But you were forming elemental iron, and they were swapping places. So if you could look at that, what you would see is that you would see magnesium giving off those electrons, and then the iron is going to pick those up, and as soon as it gets those electrons, then it's going to come out of that solution. So if you could see this, if you could shrink yourself down and see what was taking place, you'd see those electrons being given off, the magnesium is going into the solution, the iron is coming out. So over a period of time, if you could draw a graph, and you had a concentration of iron 3 plus ions and a concentration of magnesium ions, okay? So let's say you could keep track of this as a function of time, okay? So what would happen is that you would see the concentration of your Fe3 plus ions decrease, okay? That would drop. So you're going to see fewer and fewer iron ions. What you would see is an increase in the concentration of the magnesium ions, because those are going into the solution. So over the period of time, you would see a fundamental shift in the nature of that solution. So iron has a very distinctive color. It's very orangish color. So actually what you would see if you let that reaction long enough, you would actually see the solution turn clear, because the iron is being used up, and so you're going to see less and less of that, and magnesium nitrate is a clear solution. So you would actually see it change color if you let it run long enough. Okay. So with all of that said, so you have magnesium and FeNO3. Now, here's if you screw this up, this is what you're going to do wrong. You're going to go, oh, I'm going to make magnesium nitrate, and you're going to write that as MgNO3, and then you're going to put the iron out there. This is what you're going to do. I promise you, this is what you're going to do wrong. And you sit there and go, Mr. Burkamp, we won't do that. You lie, you lie, you lie. Okay? So here's the deal. You are going to make magnesium nitrate, okay? But when you make that magnesium nitrate, you have to look at it like you're starting from scratch. It's just like you're just taking the chemical formulas test. And I'm going to say, hey, Carter, I want you to write the formula for magnesium nitrate. Carter's going to go, Mr. Burkamp, I got you covered, man. He's going to look on his little chart, and he's going to go, oh, magnesium is 2 plus, nitrate is 1 minus. And then he's going to go, Mr. Burkamp, I'm going to do you a solid. I am not going to fall into your little trap. I'm a better chemist than that. I'm going to write that as MgNO3 too. So you cannot transfer the subscripts. You have to look at, you are making this thing from scratch, okay? That magnesium is going to react with that nitrate, and you're going to make MgNO3 too, plus iron. Now you have to balance it though. So you have 3 and 2. What's the least common multiple, Miles, of 3 and 2?
Least common?
Least common multiple of 3 and 2.
6.
6, okay? So you're going to come in here and go, okay, I'm going to put a 2 here so that I got 6 nitrates. I'm going to put a 3 here, I've got my 6 nitrates. And then I got 3 magnesium, 3 magnesiums, 2 irons, boom, I'm off to the races. There we go. Okay? So that's what that overall complete balanced reaction should look like. Okay? Cool with that. Got it? Good. Brain. Now we're going to go through and we're going to write the net ionics. Now here's what's important. This is elemental magnesium. This is not a magnesium ion at this point. It's magnesium. So if it's just the element by itself, it has no charge. Okay? Technically, it has what's called an oxidation state of 0. So every elemental form of a substance, the oxidation state is 0 because it has its full cadre of electrons. Okay, these electrons and those protons, these neutrons, formed in the death of a star. They're tight. Okay, they like each other. They've been hanging out, right? So when you write the net, when you do that next step, this magnesium here don't put the charge on it. It is not 2 plus. It is not 2 plus at that point. It is 0 because it's a solid piece of magnesium. So don't put the 2 plus on that one. It's not there. It's a chunk of magnesium at that point. Now, your Fe3 plus, hey, that's floating around as an ion. Okay, that's cool. Your nitrates, those are floating around. Those are down. Okay? So, again, what this step shows you is what phase these things are in. Now, over here, I'm going to make magnesium nitrate. Now, here's the difference. When I make that magnesium nitrate over there, now that is Mg2 plus, because now it's given away its electrons. Now it's existing in that solution as an ion. The nitrate's still floating around. The nitrate's going, yes, up, whatever, okay? Now, the iron, though, now we've made Iron Man. Now we've made elemental iron. So that iron over there has no charge, because now we've made elemental iron. Okay, so this is what's so important about the information that you convey in this net ionic equation. Because it says, wow, I got a chunk of magnesium, I have iron ions. I'm going to make magnesium ions and Iron Man. Okay? That's it. So this is why this conveys two completely different things. Fe3 plus and Fe are two completely different things. One's an ion in the water, the other one I can use to make a suit out of it. This is magnesium, I can burn it, and it produces a brilliant white light. This is floating around in water. Two completely different things. Okay? I cannot burn magnesium ions. Okay? I can burn a chunk of magnesium, but I can't burn magnesium ions. That's the importance of those oxidation states and the information that it conveys. Now we eliminate our spectator ions. And in this case, our spectator ions are just NO3. So now I've got Mg plus Fe3 plus yielding Mg2 plus iron. Now, is that balanced? Raman, am I done at this point?
I think so, but I'm not sure. What? Okay, stop laughing at me.
No, I was trying
Why are you crying?
because it is so not done.
Okay, I'm sorry about that. Explain it now.
Okay, what's the sum of the oxidation states on the reactant side?
Well, there's 3 on
What's on the product side?
2.
Do you think that's balanced on charge?
No.
What are you going to have to do then?
You're gonna have to put a 2 on. Oh, I don't know.
No, keep going.
A 2 on the.
With the same question I asked Miles.
Okay.
What's the least common multiple of 3 and 2?
6. So you have to put a 2.
Keep going.
Three.
Put a what where?
Oh, okay. The 2 in front of the magnesium, or
I can do that.
okay.
Okay?
And then a 3 in front of the iron.
I don't recommend that.
Okay. 2 then.
How about I put a 2 here?
Okay. Yeah, that's fine.
So if I put a 2 there, what's the total charge on this side?
It's the 6.
6. So how am I going to get a 6 over here?
3 in front of the magnesium.
Okay? Now over here in front of the magnesium, what am I going to have to put?
3.
And what am I going to put over here?
2.
There you go. Now it's balanced on both things. Any net ionic reaction has to balance on both things. It has to balance on charge, and it has to balance on number of particles. Now, here's what I want you to see is the difference. If I were making like on number 10, here's your net ionic on number 10. This is what your net ionic should be like because you produced aluminum hydroxide. Okay? So here's the deal. In this situation, you want the sum of the oxidation numbers to add up to equal to 0. Because you want on this side, that aluminum hydroxide is 0. So both sides to have to add up to equal to 0. So it's one of the things I want you to get out of your minds right now, that, oh, the oxidation numbers always have to add up to equal to 0 on both sides. Okay? If you're making a precipitate, they do, legitimately. They have to add up to equal to 0. But in this situation here, the sum of the oxidation numbers are going to add up to 6 on both sides. Okay? So I don't want you to think, oh, they always have to add up to equal to 0. Okay? They don't have to add up to equal to 0. They just have to add up to the same quantity on both sides. Okay? So that's what I want you to get out of that misconception right now. Okay? So that's like a nice contrast to show that. All right. Are there, Robin?
8. Can you go over that one, please?
What'd you say?
8. Can you go over 8?
Like the reaction, like with the aluminum nitrate and the hydrochloric acid?
No, the other 8. Yeah.
On question number 8?
Yeah.
Hold on, let me see that for a second.
She was being sarcastic, there's no other 8.
I was just gonna say, because here's why I say that, is because on the original version of this, there was a number 8 on here that I took out.
I apologize.
And that's why I was kind of flipped out, because it's like, oh, I took that question out, did it end up printing? That's why I was kind of flipped out,
Okay, I apologize.
okay?
Forgive me, sarcasm. I apologize.
Yeah, so literally, that's you just happen to pick the one that I took off that lab, and I'm going, God, did it still end up printing?
Oh no.
Okay,
Dang it. Okay, yeah.
okay, so here's the deal. So on number 8, ramen,
Okay.
you got aluminum nitrate, right? And hydrochloric acid. What type of reaction is it?
Single displacement.
No.
Double displacement.
Yes.
Sorry. I didn't see the H. I apologize.
So you're going to get aluminum fluoride. Now, here's what some of you are doing, and stop, okay? Yes, chlorine is a diatomic, okay? But it's only a diatomic when it is by itself, okay? We won't do this because chlorine gas is highly poisonous, okay? It can be actually used in terrorist attacks, okay? So chlorine gas itself, I am never going to have. Well, I can't even buy chlorine gas. It is illegal for me to have chlorine gas like on the premises, okay? Because it's that poisonous. Can't do it, okay? So what I've seen some of you try and do is you're going to go, oh, AO, and you take this little bit of information that says, oh, chlorine is diatomic. Oh, that's going to be Cl2, and but chlorine is 3. Chlorine is 1 minus, and aluminum is 3 plus, and then you come out here and you do this, okay? Stop. Bad. Horrible. Okay? The only time it's a diatomic is if you were to actually produce chlorine gas. If you were to take sodium chloride and do a decomposition and produce sodium and chlorine, then it would be diatomic. Okay? If you were to separate sodium chloride into in a decomposition reaction, then that would exist as chlorine gas. Okay? Robin?
Do you not put a 3 on the outside of the nitrate? Because aluminum.
Yeah, I am.
Why didn't you put it?
Okay. I just got wrapped up in, it's there. Yes, it is.
Okay.
Okay.
Thank you. Sorry, I was looking.
Actually, ironically, I was thinking about to mention the fact that chlorine isn't diatomic, and that's why I didn't do that. Izzy?
So with the chart and the soluble and insoluble products, are the soluble ones the spectator ions?
No. Okay. You're making too broad a statement. Okay. The only thing the chart tells you is if you put it in water, will it separate out?
So do I just put like yes or no, or do I check soluble or insoluble? What am I supposed to put in those boxes?
Hold on. Okay.
How did you get that?
Izzy,
Look at the
let me get
products.
done with this one, and then I'll get back to you. Okay? Yes?
Would hydrogen gas be considered a precipitate?
Not necessarily a precipitate, but a new product.
Yeah, but would you want to put that in soluble or insoluble? Because
It's got.
Technically, it's insoluble because it's a gas. It
Yeah,
doesn't dissolve.
okay.
Yeah. Okay. So let me finish this one. So, Ron, focus. Okay.
Okay.
So then you're going to get nitric acid, HNO3, right? So all of these products over here are soluble. Okay? The aluminum chloride is soluble, the nitric acid is soluble. So the only thing you have to do is just balance that reaction, because you're not going to get a precipitate out of it.
You put a 3 over the last one.
Well, you can
And
do
then a
that,
3 on the hydro-
because you got 3 chlorines, so you need 3 chlorines, right? But then you need 3 hydrogens over there, but then that gets you 3 nitrates, and you have 3 nitrates on the other side.
Yeah.
Yeah,
Yeah.
yeah. So,
You seem very, you were like, it's not. And you have this tone where every time I say.
I know, I
something,
never
you guys-
have tone. I never have tone.
Be quiet.
Okay.
No, but Lincoln does a side.
You start crying whenever I answer my phone. I'm sorry if I don't understand something fully. Don't make me feel bad. I'm like, that's-
Oh, for the love of God. I can't even, no, no. Okay. So on the chart, okay, speaking of the chart, all right? So what was your question? I thought I went over it. So what is your question?
Oh, that's it? That's all I So we just stop there?
Yeah.
So on the one above it, do we just stop there too?
Yes. Because there's no precipitate. So on 7 and 8, just right on that third line, just put no precipitate. Yes.
Is there a precipitate on 4?
On 4,
No.
Oh.
you just make water. So on 4, yes,
Is water considered soluble or insoluble?
that's like asking is water wet?
Yeah, but like, what
Okay.
column?
It's not really soluble or insoluble, but it's a new molecular product. So we include it in the net ionic.
But like on the chart.
You can just put it as soluble. You can put it on either one. I don't care.
Okay.
So Emma asked about on number 4. Okay? So this is a classic what we call a neutralization reaction. You're neutralizing an acid and a base. So you have sodium hydroxide and hydrochloric acid, and you get salt water. Okay? So out of a neutralization of an acid and a base, you get 2 products. You get water and you get a salt. Okay? If this had been lithium hydroxide and nitric acid, I'd get water and lithium nitrate. Okay? So a salt is a generic term for the cation and anion. It's a generic term. Okay? So out of any neutralization reaction of an acid base, you get water and salt. So the sodium chloride is soluble. Okay? So your new product is water because that's the molecular form. So your net ionic equation is just that. You're just making water. So in terms of soluble or insoluble, it isn't, that really doesn't matter. The main thing being is that you are forming a new compound. You took a separate hydrogen ion and an OH ion that were existing separately, and then they're joined together. So you are making a new product, okay? But it just really isn't soluble or insoluble. It's just, you're just making a product. So on number 4, that's your net ionic reaction right there. You are making water because it's a net ionic because you took 2 separate ions and you joined them together. Carter,
Do you not need to balance this?
that is balanced.
He means like with the H's on H2O.
There's 2 H's on the left side.
Yeah.
Oh, because there's 1 H on the H and then 1
Yeah.
H on the H.
Here's a hydrogen, there's a hydrogen. There's 2. There's 1 oxygen.
There's 2 hydrogens on that
I
side.
got this in
You literally had the same question.
I'm gonna cry.
Oh no, that's my job. If anyone cries in here, that's me. Okay?
Wait, that's right. Really bad.
What'd you do today? We made Mr. Burkett cry. Really?
MG in it.
Okay. Now,
You're gonna do that on your own.
let's talk about the question, that first question 1 says, could any of the reagents be used to cause the calcium ion to form a precipitate? Okay? So here's the deal. So you have a calcium ion, right? You want to somehow make that precipitate out. So is there something that you could add to that, so when you look at your solubility rules, that could make it form a precipitate? So if you look at your, what we call reagents, so you got to get used to the terminology of chemistry, okay? So reagents are things that you add to start a reaction. So you had 3 reagents, okay? And they're listed up there on that chart, okay? So you have 3 reagents. You have hydrochloric acid, you have sodium hydroxide, and you have ammonium hydroxide, okay? Those are your 3 reagents, okay? So basically, start with this. If you took a calcium ion and reacted that with hydrochloric acid,
What number are you on?
One of the questions.
number 1 of the questions, okay?
Okay.
So,
The second set of questions.
yeah, that number 1 where it says, could any of the reagents be used to cause the calcium ion to form a precipitate?
I didn't even know those were.
These are these ones.
Where?
4.
Yes. Those are the questions that you have to answer
Yeah, I didn't
Another
see
1
that.
through 5.
on a whole other sheet of paper, okay? Do not answer 1 through 7 on this strip of paper, so help me, I will flip out. You answer those on a completely separate sheet of paper, okay?
Oh, snap.
That's really
You're
awkward.
joking.
Did you give us a little work time?
Mr. Birdcamp, we already have it on the paper, he used to be good.
How? Okay, here's the deal. You all have been my students now for almost, what, 3 months? Okay? Whenever I want you to, on a paper, if I wanted you to answer it there, what do I do? What do I always give
Put
you?
lines.
I give you lines, I give you spaces. You know why?
Well, you should
So I don't-
specify.
Because it makes it
I
easier
don't
for me to
care. You
grade.
didn't tell us
Why
why.
didn't you
Okay?
give us space?
If I wanted you to answer that on that sheet, what would I have done?
Put lines.
Why didn't you put
Yes.
lines?
Did I?
You gave us a whole backside. I don't.
Okay, I can live with the backside, but just not right here, like right beside the space.
You know what? Next time, let us know.
For the love
I didn't
of.
even notice those questions. Oh, the love.
I didn't know those were questions.
Me neither, because there's.
What did you think they were? Just
I don't know.
random words?
I thought it was like the lab
words, I'm not
directions.
reading. I'm just gonna be real.
Yeah.
Huh?
Stop
Can we
yelling
have
at
another
us.
day?
I'm not yelling.
You are yelling.
I'm just talking loudly.
I'm trying to.
Can you go over number 4?
Okay, let me
Which
finish
one?
number 1, then we'll talk about
number
number
1
There's
first.
3
Yeah.
number
Okay.
Yeah, which
4s.
one?
What?
Can you email this video to me?
It's on YouTube.
Oh,
Go
wait,
subscribe, everyone.
Oh,
Stay
okay.
on the
Subscribe.
breakout.
I'm subscribed.
okay,
Press the like button.
I'm
and
subscribed.
subscribe.
okay. Anyway, back to, let's talk about question 1 that's going to be answered on another sheet of paper.
Question.
Hey, I wasn't the only one.
No, definitely not.
Everybody did it.
What?
I'm glad I got it.
That's not even a question.
Yes, it is.
Perform the 12 reactions listed on page 1.
Okay, that's not a question.
Okay, let's answer that. Got it.
Okay,
He's gonna retire after we
Oh, this
so here's the story.
He's gonna retire.
If you tried to make calcium chloride, is calcium chloride soluble or insoluble?
Soluble.
Soluble. So if I put it in hydrochloric acid, nothing's going to happen, okay? Or it's going to, nothing, you're not forming a precipitate. But if I introduced hydroxides into it and made calcium hydroxide, is calcium hydroxide soluble or insoluble?
Insoluble.
Insoluble. So you could either use sodium hydroxide or ammonium hydroxide. So a lot of times, and when you get into more complex labs, what you do is what's called a differential precipitation. So if you have a test tube, and then when you can get into this later on, where you have an unknown number of cations in the solution, what you have to be able to do is separate them out. So if you had a test tube, say for example, and it had sodium ions in it and you had calcium ions in it, okay? And you wanted to separate those out. They're mixed together. So what you could do is add sodium hydroxide to it. So what would happen is that the hydroxide would bound up with the calcium. So what you would see is at the bottom of the test tube, you would have a solution of calcium hydroxide down here, but then the sodium ions would exist up above. So if you were given a test tube and say, hey, I got sodium ions, I got calcium ions, how can I separate them out? Well, we can't grab a pair of tweezers and just randomly pull them out. So we find something that will make a precipitate with one and not the other. Okay, so question number 4. And this is the same type of thing. So describe a procedure you could use to differentiate between two test tubes, one that contains silver ions and ones that contain iron. So imagine this. I gave you a test tube. One has silver ions in it, and the other one has iron. Put it Fe2+, doesn't make any difference. Okay? So what you want to do is find an anion that will form a precipitate with one of them, but not the other one. Okay? So if you look on your solubility rules, for example, with silver, okay? If you look at silver, there's one particular ion that is mostly soluble except for silver and lead. But with that same one, with the iron, it'll be soluble. So, and this is what you're going to be doing in your lab final, okay? You're going to be given ions, and you have to figure out what they are. And so one of the things you got to be able to do is differentiate and look at a chart and figure out, okay, what's something I can react with one that will react in a particular way that it won't react with the other one. So, with that being said, what's an ion that will react with silver to form a precipitate, but it won't react with iron to form a precipitate? All right. So you can say, hey, I'm going to add hydrochloric acid to both test tubes. The one that forms a precipitate will be the silver ion. The one that doesn't form a precipitate is going to be the iron. Okay? Now, and you want to go through that when you're asked to describe a procedure. Just don't say, oh, I'm going to add hydrochloric acid. That's not a procedure. Okay? That doesn't tell you anything. You want to follow that thought process through and say, oh, if I've got this, I add the hydrochloric acid, this is the precipitate that will form. It won't form a precipitate with the other one because that's soluble. So just don't say, oh, I'm going to add hydrochloric acid. It's too vague. You want to say what's going to precipitate out and what won't. Okay? On 5 and 6, I promise you, you've got to be able to do these molarity calculations, okay? It's one of the most important skills you have to have coming out of this class. If I let you walk out of this class and you can't do mole conversions, I have done you a huge disservice. So let me give you some hints. So, and this is the real practicality of it. Like literally, this is what I did when I mixed up this lab. These are the exact calculations that I did. Okay? So, let me give you some hints. On number 5, first off, you have to start off with the correct formula for iron 3 nitrate. Okay? If you don't start off with the correct formula for iron 3 nitrate, you are dead in the water. Okay? You just can't do anything. So, your answer to number 5, okay? The mass of iron 3 nitrate that you need should be around 20 grams. Okay? So how you want to answer number 5 is that you're going to say dissolve about 20 grams of iron 3 nitrate in enough water to make 100 milliliters. Okay? When you say describe the preparations, it is a statement. Okay? You're going to say dissolve whatever that mass is, pretty close to 20 grams, of FeNO3 and enough water to make 100 milliliters. It's like you are going to Grace, and you're saying, Grace, it's like you're telling her, Grace, this is what you need to do. Grace, you need to measure out this amount of water, or this amount of iron 3 nitrate, and dissolve it in 100 milliliters of water. It's like you're telling someone what to do, okay? On number 6, that mass of sodium hydroxide should be around 5, okay? So your answer to number 5 should be around 20. Your answer to number 6 should be around 5 grams. Yes? Huh? Yes. On number 7, when you're finding the number of atoms in that strip of magnesium, that answer should be something around 10 to the 21st. Pretty big number. There are a lot of atoms inside that strip of magnesium. Okay. Anything else on the laugh? That was painful. Grace.
Oh, you're fine.
So, what?
You know how many gray hairs I got today? Do you have any idea?
Boy, do you have-
Fine.
Boy, you seem to give us every day.
Anyways,
Anyway, Grace.
what goes in, I'm like confused about what we're putting in the boxes with the reagents.
What do you mean?
Like, this one, I already know what she means.
Yeah.
They're reagents? I already know.
Okay, hold on. When so you have 3 reagents, hydrochloric acid, okay,
You're supposed to write down what.
NH4OH, and sodium hydroxide. Okay? Those are your 3 reagents. Underneath there, you're going to list anything that formed a precipitate or made something new. So like under the hydrochloric acid, for example, you made a precipitate of silver chloride. Okay? Underneath the ammonium hydroxide, you should have made the precipitate of copper hydroxide. Underneath the sodium hydroxide, you would have made a precipitate of AgOH. Now, that isn't the complete list. This is, so what you're going to do, okay, you're going to go through those 12 reactions, and you're going to list anything that made a precipitate with hydrochloric acid or formed a new product. Like, for example, that hydrochloric acid made hydrogen gas, so put that in there, okay? So you're just going to go through the list, find all the reactions that had ammonium hydroxide, and see anything that made a precipitate. Then the same thing with the sodium hydroxide, and you're just going to list those out, okay? That's all you have to do. Do not make it complicated.
Okay. And
Yes.
Also, what's the difference between like the reagents and like the catalyst?
Okay, what happens in a catalyst? So let's say we did that reaction with hydrogen peroxide, and we had a catalyst of potassium iodide, and that decomposed water into water and oxygen. Okay, so here's the difference. A very good question. So a catalyst is there, but all it does is speed up the reaction. It's not actually involved in the reaction. So it's kind of like you're at a track meet, and a good friend of yours is running in a race, okay? And you're trying to be the catalyst to make that person go faster. So you're standing on the sideline going, come on, run, faster, 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 okay? You're not involved in the race,
Oh, it's the hydrogen.
but you make that person go faster, okay? So hydrogen peroxide will decompose naturally into water and oxygen, but it's a very slow process. So it's like this person is walking really, really slow around the track. Potassium iodide makes that reaction just go really, really fast. So that's like you yelling and going, hey, go faster, okay? Now, a reagent, like for example, if you have sodium hydroxide and, I don't know, silver nitrate, okay? A reagent is actually involved in the reaction. Okay, so a reagent is going to be part of what's taking place. So a catalyst is there, but you're standing on the sideline yelling at the person. Okay, a reagent is actually part of the reaction. Okay, does that make sense? Okay.
Ammonium hydroxide.
Oh my gosh.
Okay. Yes, if this causes me to have more gray hair, so help me.
I was just wondering which one.
Hold on.
1 meter.
What'd you say?
Which reagent formed the least number of precipitats?
That ammonium hydroxide by far and away.
Is that just because it was involved in the least number?
Yeah.
Okay.
Yeah.
Cool.
It's ammonium.
I just threw that one in to get you used to the ammonium ion. I could have done this all with the sodium hydroxide, but I threw that in to get you guys used to seeing ammonium.
Oh, it's in
Oh, looks like it's time to go.
For ammonium.
It's not even close to time to go.
We have 50 minutes.
Oh, no.
I'm pretty sure.
Okay, any other questions on the lab?
Yeah.
What?
I'm joking.
Okay.
No, actually, oh, do we get like, do we get some like
That
sounds
You probably make me look stupid.
You have the sign for tomorrow.
Dude.
Okay.
Not dude. Mister. Sorry.
What? Okay. So the test coming up on Monday. So we'll review tomorrow, okay? So you won't have any homework tomorrow night. It's just going to be getting ready for the test. So this is going to tell you basically how prepared you are for the test. The only thing on all of these, the only thing I've done is giving you the reactants, okay? You have to figure out what the product, and there is every type of reaction on here, okay? Every type of reaction is here. Some of these are not going to occur, okay? And I tell you that in the instructions. Some reactions aren't going to take place. So you have access to a wide variety of resources. You're going to have to use your solubility rules. You're going to have to use your reactivity series, okay? You're going to have some decomposition reactions of aluminum chlorate, okay? So if you don't remember how aluminum chlorate decomposes, look in that packet. It says, oh, here's how chlorates decompose, okay? So what I want done, like H3PO4, hey, phosphoric acid, okay? Here it is. So what you should be able to do, use this as a simulation of the test, okay? Now, on this particular one, there are no net ionic equations. All these are just your standard run-of-the-mill balanced equations, okay? So don't worry about doing net ionics on these. Yes?
That means no charges.
That means no charges.
Hallelujah.
Now, you have to keep track of them. So like on the first one, you're going to take lithium and you're going to burn that with oxygen, okay? So when you write lithium oxide, you have to worry about that.
So the subscripts still matter.
Oh, yeah. Oh, yeah. So like the first one, one of these, you're going to have lithium plus oxygen, okay? So here's what I don't want you to do. Just don't go, oh, Li plus O yields LiO. Okay? Horrible. It's a train wreck. It's horrible. Okay? First off, you have oxygen gas. What do you know about oxygen gas? Monoatomic, diatomic.
diatomic.
So you got to put that as Li2O, right? Now, when you write lithium oxide, what's the charge on lithium? 1. It's an alkali metal, okay? Oxygen, that's 6 valence electrons. So lithium is 1 plus, oxygen is 2 minus. So how are you going to write lithium oxide?
Li2O.
Li2O. Then you got to balance it. So you do have to worry about them,
You
okay?
don't have to write them.
But you just don't have to write them out. They're part and parcel of the process, just not in terms of writing the net ionics. Now, on the test, yes, you're going to have to do net ionics, just not on this. Okay. Stop you on the camera.